Based on the selected topic, find an example of the problem that can be formulated as n linear programming. As you can see, the problem are shown as below. Below is the objective function where we can see the maximum z is 0.08x1 plus 0.1x2 plus 0.14x3. They have 4 constraints. The calculation of table 1 is as below that you can see. This is the table 2. This is the table 3. And this is the table 4. The optimal solution of z is 18,100, x1 is 6,250, x2 is 6,250, and x3 is 121,250.
Okay, Assalamualaikum. Now I'm Sofia Dini and I'm going to present about the second question is write a manual report on solving this LP step by step by using Microsoft Excel Solver or Lindo. Please include the print screen of each step in the report. For our group, we choose to use Microsoft Excel Solver. So these are the step by step that we provide to this problem. The first step is we have to add in the solver in our Microsoft Excel. So the first step is we click options, then we click add in. For that, this will show this, and we will need to choose solver add in. This is solver add in, and then we click OK. So our solver was add in our Microsoft Excel. The second step is write the column for variable and then highlight the box. So as you can see, we write variables in A1 box and then we highlight the box. The second step is enter all variables x1, x2, x3. Why we have 3x? Because on the in our objective function, we have x1, x2, and x3. So we put x1, x2, x3, and then we write all zeros beside the variable columns. So x1 is 0, x2 0, x3 0. The fourth step is we write the objective column. Then, okay, this is objective column. We highlight that. Then we enter the function z. So the objective function of the maxima z is 0.08x1. So this is 0.08 time. Why we click this B2? We click this B2 because this is the x1. You can see this x1 is equal to 0. So we click B1 is equal to 0.08x1 plus 0.1x2, 0.1 time B3. B3, as you can see this is x3 plus 0.14 B4. We click B4 because for the x3. Okay, the next step is we write constraints. Okay, this is constraints, and we highlight the box. Then write all the total constraint in a column. So we have the total of 4 constraints, which is x1 plus x2 plus x3 is less than or equal to 250,000. The second constraint is x1 less than or equal to 6,250. The third constraint is x2 is less than or equal to 6,250, and the last constraint is 0.06 x2 plus 0.1 x3 less than 12,500. So as you can see, okay, we write inequality here, and then we write the first constraint. Okay, the first constraint is x1 plus x2 plus x3. So we click B2 for B1 for B2 for x1, we click B3 for x2 and B4 for x3. Okay, then we click enter. After we click enter, this automatically shows 0, and then we write the sign less than or equal at the below of inequality column. Okay, here you can write like this, and then write the value of right hand side. So the value of our right hand side is 250,000. Okay, so we write the right hand side number 250,000 here at the below of the right hand side box. And then after that we enter all the second, third and fourth constraint. So this is the first constraint, and this is the example when we have done to write all the constraint for the first constraint, second constraint, third constraint and fourth constraint, as you can see like at our problem. Okay, the sixth step is we have to click data tab. Okay, this is the data tab, and then we click the solver. Okay, the solver that we had at the beginning of our step. So this is the symbol of our solver, as you can see this. Okay, you click this. Okay, then we set our objective. So our objective, we click on B8. Okay, B8, this is our maximize that we write before this. Okay, we click this, and then we choose the maximize, the max, because for our objective function, the question asks for the maximize function. So we click max. Okay, then at the column of by changing variable cells, we select all 3 variables, which is x1, x2, x3. So we choose B2, B3 and B4. We highlight this, and then for the subject to constraint, as you can see at the larger box here. So first we click add. Okay, this is add the first cell reference, so after we click add, it will show like this. So for the first cell reference, this is cell reference, we click B12, which is our first constraint. And then for the constraint, we click D12. D12 is our right hand side for the first our constraint. So we click OK. We click add. After we click add, then we enter all constraints until the fourth constraint. So the total of our constraint have 4. So we add all the constraints and finally we click OK. So all the constraints are here in the subject to the constraint. As you can see here. Okay, so we select a solving method. We select a solving method here. We choose simplex LP, which is simplex linear programming, and then finally we click solve and then OK. So this is our solution. The x1 is equal to 6,250, x2 is 6,250, x3 is 121,250. For our objective, the maximum z value is 18,100. So this is our optimal solution, the value of x1, x2, x3 and the maximum value. So thank you.
In detail the sensitivity analysis by giving at least 2 examples for each cases when there are changes on right hand side. To express the optimum simplex tableau of the modified problem in terms of change D1, D2, D3 and D4, we first rewrite the starting tableau using the new right hand side. This is the initial tableau that have been added for the changes. This is the optimal tableau. New optimal tableau provides the following optimal solution. Dual price. New objective function can be written as feasibility range. The current solution remains feasible if all the basis variables remain non-negative. Case 1. Substituting in the feasible condition, we get hence the current basis remain optimal with the new optimal feasible solution value are. This is the feasibility range for D1. This is the feasibility range for D2. This is the feasibility range for D3. This is the feasibility range for D4. The dual price and their feasibility range for the LP can be summarized as in the following table. Case 2. Substituting in the feasible condition, we get since S1 is less than or equal to 0, hence the current solution does not remain feasible. Addition calculation will be needed to find the new solution.
When there are changes in the objective function coefficients, we need to find out the objective function from optimal tableau above. From this slide, original objective function will add with small letter d represent the changes on the function coefficient. When BV always 0, reduce cost for NBV, which is S2, is addition of column S2 multiple with first column. When BV always 0, reduce cost for NBV, which is S2, is addition of column S2 multiple with first column. Continue the same calculation for NBV S3 and S4. Thus, the simultaneous optimality condition corresponding to NBV S2, S3 and S4 is greater than 0 based on equations. For case 1, there are changes in objective function, so new objective function minus original objective function to get small letter d1, d2 and d3. Substitute the changes into the optimality condition above and consider satisfied when NBV is greater than 0. This shows the proposed changes will keep the current solution optimal, but with a new value of Z which is 22,112.5. To find optimal range for D1, assume D2 and D3 equal to 0. Then substitute the value of D2 and D3 into optimality condition. Repeat the same steps to find optimal range for D2 and D3. The table shows the optimality range for variable x1, x2 and x3. For case 2, same goes to case 1. There are changes in objective function, so we need to find D1, D2 and D3. Substitute the changes into the optimality condition above and consider satisfied when NBV is greater than 0. To show that the proposed changes will keep the current solution optimal but with a new value of Z, which is 7,975. To find optimal range for D1, assume D2 and D3 equal to 0. Then substitute the value of D2 and D3 into optimality condition. Repeat the same steps to find optimal range for D2 and D3. The table shows the optimality range for variable x1, x2 and x3.